Okay, thank you very much for joining everyone for our newest edition of our Lift Technology webinar series. Today we're going to be talking about the best practices and control of welding-induced distortions and lightweight metallic structures. We are lucky enough to have Dr. Pingsha Dong from the University of Michigan, who was integral in this project with our team here at Lift. So you will learn a lot from him today, so we're looking forward to him, and thank you for joining, and thank you to Pingsha for presenting today. Wanted to give you a little bit of background on Lift before we hand it off. We are a public-private partnership that is funded in part by the Department of Defense, as well as industry members around the country, and we are managed through the Office of Naval Research. Our focus is on lightweighting, so we believe that our mission is revolutionizing manufacturing through innovation, collaboration, and education workforce development. We believe that if it moves by air, land, sea, or in space, it can be lightweighted. And so we really operate in three different avenues. We operate in technology development, technology transition and transfer, and education workforce development. So those are the three focus areas that we have as an institute. We are based here in Detroit, Michigan, along the I-75 corridor. Our initial territory, we are a national institute, but we had an initial territory of Michigan, Indiana, Ohio, Kentucky, and Tennessee. Those were where 50% of the metalworking jobs were in the country. And as we focused on lightweight metals, we thought it appropriate to be here in Detroit, in the Motor City, and along that I-75 corridor. We do have a 100,000 square foot facility here in Detroit that we share with another institute that focuses on composite materials, the IACME Institute. We do have capabilities and machines out in our high bay that we invite you to come and see. You can see some of the capabilities on your screen now. We invite you to come over to Detroit and visit. We will give you a tour and have you talk with some of our engineers and some of the technicians that are involved in the back. They're doing work, everything from powder consolidations to thermomechanical processing to flexible manufacturing and characterization, as well as an advanced machine shop. We're also in the process of installing the largest linear friction welder in the country. That is going to come online here within the next month, we believe. Our friends at MTI down in South Bend, Indiana, have been working on this for a long time, and we are very excited about the capabilities that we'll have there with the linear friction welding. We are also a leader in education workforce development. As people have heard, there is a tremendous skills gap in manufacturing and engineering. Not enough folks going into that as a career choice. So that is why that is one of our focus areas. So we've made more than 40 investments that are replicable and scalable and sustainable around the country, engaging 150 education workforce partners and impacting nearly 200,000 teachers and students around the country. We are in the process, again, here at our facility of building out the Lift Learning Lab, which is a unique facility that will house training opportunities and certification opportunities and really just exposure opportunities to the world of advanced manufacturing for teachers and students that may just need exposure to the world of manufacturing, to teachers who can take some of what they learn back into the classroom, to incumbent workers who just need to be upskilled or earn some certifications. So we're looking forward to that coming online later on this year, hopefully in the first quarter. As I mentioned, you can come visit us here at Lift. We're at 1400 Rosa Parks Boulevard in Detroit. You can always learn more a little bit about our technology programs and our education workforce programs on our website at lift.technology. And you can follow us on our social media channels, Twitter and Facebook and LinkedIn at News from Lift. LinkedIn is actually Lift Lightweight Innovations for Tomorrow. But you can follow us on Twitter at News from Lift, or you can give us a call, and we'll be happy to put you in touch with any of our experts if you have questions about what we have going on. Finally, I want to invite you next week. We are hosting an event here, a technology and tour event, leading into the North American International Auto Show. We're going to have a half-day event here to talk about many of our melt processing projects, some of the successes that we've seen in that pillar of technology. from noon to 5 on Tuesday the 15th. You'll hear from some of our network of experts. You'll hear a little bit about our melt processing roadmap as we look into the future on how that processing technology can be used for lightweighting going forward. We'll give you a tour of the high bay. So please visit lift.technology, and under the events tab, you can find the technology and tour event for the 15th of January. So please go ahead and join us for that. We look forward to having you here. So with that, I wanted to introduce Ping Shaw. I know he can take care of introducing himself, but by the way of housekeeping, I want to make sure that your phones are on mute. If you do have a question, he and I talked, and you can feel free to chime in if you'd like, or you can use the GoToMeeting chat function. That is the chat window that's on the right-hand side of my screen. You can address the question to the organizer, and that question will come to me, and I can facilitate the Q&A that way as well. So a couple opportunities to ask questions for people. You can chime in if you'd like, or you can reserve that question and type it into the GoToMeeting chat function. Also, this webinar is being recorded, so again, that's another reason we put our phones on mute, just to make sure there's not any background noise, and then we can share it, and you can share it with your friends and family who are unable to make it today. But without further ado, I want to introduce Dr. Ping-Shaw Dong from the University of Michigan to talk us through the distortion control process that he and the team went through. Ping-Shaw, I'm going to give you the presentation now, and it is all yours.
Let me take that over. Okay, share screen. Can you see my screen?
I can.
Yes.
That looks okay on the screen?
It looks good. Thank you very much.
Okay. Just quickly, I'm with the University of Michigan. My name is Ping-Shaw Dong. So I'm with the position of mechanical engineering, also naval architecture. I'm also leading global automotive manufacturing engineering programs. In the meantime, on the research educational side, focused on welded structures. Okay. So here's what I plan to talk about. I think given the time available, I'll try to keep things simple and to the point, focused on the application side of things. So here's only going to be a few minutes talk about what my group does. Essentially, I lay the background, say how some of the argument I can make, how some of the simple solutions developed over the years based on advanced research, but the application side can be rather simple. So the second point is why distortion control become very important today. I think you already touched upon, say, the lightweighting really become very challenging, particularly from dimensional accuracy control point of view. And with that, we need to understand a little bit how distortion get developed. What is the underpinning mechanics? Knowing that actually the distortion control technique can be described just by a few sentences, not that complicated, but the actual implementation can take many different forms. So that leads into basic principles for distortion control. So how to, based on understanding of the mechanism, how we can implement for different applications, different structural forms. So with that, I'll share with you some of the examples to demonstrate how those principles can be used, and with some concluding remarks. Just quickly, over the years, I think some of you in the audience has worked with me in the past, so you have some of you may have seen this. So this is essentially still what my group does at the University of Michigan, and I think I did the same thing at Battelle, so over the last 20 years. Again, this chart not get updated properly, but at least give you a sense what my group does in terms of research and education. So this chart, what I'm trying to illustrate is we look at how material get processed, how the heat material interact to give us the quality definition we typically observe. And then along with it, we can look at the reduced stress distortion, look at the structural level, what type of distortion mechanism get introduced, how to control it. The bottom part looking at how to define quality, some of the unique simulation method, or some of them analytical, some of them computational. So I think some of you are probably familiar with some of the terminology like a Verity. It's already in the commercial market for last since 2006. And some of them continue to be the research tools my researchers or students continue to enhance, like look at the microstructure evolution, look at how they contribute to defects. So this, all the red color indicating some of the unique predictive tools we developed over the years. And the illustrations, they are taking out from some of the ongoing or past projects. So they are not cartoons, they are actual taken from actual project reports. So again, as I said earlier, I'm not going to dive into the detail. This is just showing the background. We have had opportunity looking into all aspects of welding joining, how they interact with the material, how they interact with the structure. So today we'll be focused upon distortions, okay? Previous chart is dealing with fusion processes, and this chart dealing with solid state processes. Again, we look at how nugget get formed, how induction heating interact with the welding process, interact with the material. So we introduce, build upon commercial code, ANSYS, Abacus, develop a driver system so can do electrical, thermomechanically, incrementally coupled processes. So based on those analysis, those findings, we'll be able to come out with a simplified description of the dynamics of the process, come out with some engineering applications. Again, the red color indicating implementations, how to work with the commercial code, and then in problem solving, and also come out with simple analytical argument for product-related applications. So this chart covers all solid-state processes, obviously friction stir, spot welding, diffusion bonding, and all other joining processes. So that's up here. I'm not trying to emphasize you had to do extensive computation in order to solve a problem, but this is only try to illustrate when needed, we can dive in deeper to understand the underlying mechanics, and then extrapolate from that, come out with a simpler, effective solutions. So this is just two charts highlight what my group, the researchers and PhD students, has been and continue to be working on. So with that, let's come back to the main topic. So why we are interested in distortions? Because distortion today, we're dealing with lightweight structures, high strength material, and then what happens, the material plate can become inherently stable, even though most of the distortions occurring at the welding stage, but actually welding is not the only culprit, because when you deal with thin gauge material, other processes become important. So here's the example already in the literature from one of our early projects. I think a couple of people online, they're familiar with this chart. So if I consider two flat plates coming in, they come in flat, but it's slightly different in mill condition. We normally ask fairness or flatness. We don't ask what takes to get that flatness. So then you go through simultaneous slitting. What happens on the left-hand side, you have buckling distortion immediately after slitting. Slitting essentially doesn't produce any heat, doesn't produce any significant plastic deformation. Identical slitting process on the upper right, we see the plate essentially flat. So what that says is, as we get into structural lightweighting, we have to worry about when we specify sheet, purchasing sheet or plates, we have to be mindful what process going into it so that we don't develop the situation on the left-hand side. So this is just an illustration of the situations we run into in practice. Another one related to shipbuilding. Shipbuilding also go heavily into lightweighting to reduce weight, increase performance. So this is actual ship board panel. This is about 50 feet long horizontally, I think roughly about 40 feet vertically. And the different color other than yellow indicating local reinforcement to achieve lightweight. You want to put an insert in so that it can carry reduced local stress concentration so you don't have fatigue issues. But this particular design did not have the producibility or manufacturability in mind. So there was a tremendous lesson to be learned from this example. But this took about 20 minutes to design this panel, but took about 2 weeks, okay, to get to the panel to the point even without putting stiffener on. Obviously, this is significantly grossly exceeding the design tolerance in terms of outer plane distortion. Again, on the right-hand side, you see that's a panel before. Those left-hand side, those locations indicating stiffener. With the plate condition like that, you cannot put anything on it. Right? So this is in some cases, we do need to have an insert, but this excessive use of insert in order to achieve the lightweight, but it causes tremendous issue in producibility and cost, obviously time to completion. So this is an example well documented in the literature from one of our earlier programs. Another one, I think again, in automotive industry, I think a lot of you are from automotive companies or suppliers. Friction stir welding has been done, well accepted and considered as a new solid state joining process with a low temperature, tend to give you good dimensional accuracy. In literature, friction stir welding get considered as a low stress, non-distortion technique because you go through heavy clamping as the structure is inherently structurally stable. After welding, they tend to stay in shape. So this is from Marshall Space Flight Center as a part of the Orion rocket program. There's a simulated component. Obviously, I cannot show anything related to actual component. So this is a test article. So before friction stir welding of 2 rings, in this view, you cannot see, but actually each half is about 6-7 inches wide. It's about 6 millimeter thick. Before welding, everything is the circularity, everything looks good. After friction stir welding, you can see the friction stir weld. What this says is, even if after friction stir welding, you can still develop Buckling distortion. That means there's no such a thing as a low stress, non-distortion techniques. Actually, as far as the reduced stress peak value is concerned, there's no difference. Theoretically, I'm going to get into shortly, no difference between friction stir and arc welding, except the welding conditions different because you impose quite a bit of fixturing. You go through all kinds of trouble to clamp it. But the clamping is okay as long as you are in the fixture, but after taking out from fixture on the right-hand side, so you get this pretzel type of a shape. So that means there's instability because this ring has a structurally inherently unstable, and the only thing need to trigger that instability is a shrinkage force as a result of reduced stresses produced by friction stir welding. So this is another example. And then more complex example, this obviously you can see this is not from laboratory, this is from some companies' shop floor. So by design, this is called elbow component and supposed to have a high precision. And this design, you can see the profile supposed to be square everywhere and with the internal members. After welding, you can, without any measurement, you can see what the shape look like. Right? This will grossly exceed the design tolerance, and so that case need to be fixed. So actually, lower left corner showing how this particular position, how that location look like in terms of auto tolerance. But actually, for this component, because of the poor design, the design engineer did not consider how this get built. That means the design not for distortion control. Actually, this component cannot be fixed, okay, cannot be corrected because this is related to the application is very sensitive to heat. Even if you can apply heat, you can apply local bending, but the structure inherently unstable. Again, that because the lack of structural rigidity, lack of diagonals. I think in shipbuilding we call transverse frame. It doesn't have that. So this type of design just simply cannot be built to the accuracy intended for this particular application. Okay, so this is another. We'll come back to it. Say how to fix this problem during production. Obviously, this one cannot be fixed, but the future product can be fixed. We had to introduce interim or temporary braces in order to maintain shape And once you be able to maintain shape, structure, and then the rigidity, and then you can manage the sequence. At this stage, there's nothing you can do. So this is wasted. So anyway, with that in mind, say obviously so far we talk about dimensional accuracy, dimensional variation, just for modular assembly, because modern production, modular design, modular assembly, if a thing doesn't fit, you won't be able to put them together. But actually, dimensional accuracy can have a significant impact on structural performance. There's another incentive for lightweight structures. We had to worry about what is the impact on performance, even if you manage to build it. Again, this is from most recent research investigation. Consider, say, this is ideally we define cruciform joint. This is for U.S. Navy. So you have eccentricity between the member that could be due to distortion misaligned, and obviously angular distortion, which we're going to get into, is alpha. If you look at those geometry, look pretty benign. But actually, if you derive the stress concentration factor, that's 3 times E over T. So in that case, this factor of 3 can significantly decrease fatigue life. And that can be observed by the Welding Institute test in UK. They consider, say, visually almost no distortion for 100 plus minus 100 megapascal loading. You have 7 million life and 3.6, 2, and 1.3. So you're getting close to order magnitude once this E over T about 30%. So that means there's an additional incentive to control the distortion to reduce poor fit up during assembly, because they has a tremendous distortion can have a tremendous impact on product's life. So with that in mind, most recent trend, I think lift is driving this message in terms of lightweight, and also one of the most effective way to achieve lightweight is multi-material structure. So I'm using obviously this DOE program. And again, most of you are automotive experts, so correct me if I make any wrong statement. So if you simply introducing, just consider high strength steel, the weight reduction is limited about 10%. But when you introduce multi-material, that means could be composite, aluminum, and high strength steel, depends on where they're gonna go. You should use right material at the right place. This is DOE vehicle for study. Obviously, Boeing been doing that, 787, and also most recent aircraft, there's Airbus 350, essentially follow Boeing's example, introducing a lot of composites and then in addition to material. So those different color indicating different material. Obviously, they pose additional challenges, how you put them together. Direct joining is much more desirable than mechanical or using adhesive. But once you use direct joining, you introduce plastic deformation and introducing heat, they cause distortion. So that's make it more challenging when we talk about multi-material. Again, I personally involved the UNR titanium T-craft. So there's a multi-material involved in the internal, and that can become very challenging. Okay. So with that in mind, this is try to set up the scene, say why we should worry about distortion more so today than before. Just in a nutshell, say as the way to achieve lightweighting, we got to decrease thickness. Thickness, actually, the buckling distortion we have seen from the friction stir welding example, from the shipboard buckling example, that the distortion resistance, essentially in terms of stress, is proportional to T squared. So that's why in shipbuilding industry, also in armored vehicle, when you talk about lightweight, so let's use a simple number. So if you originally, before you use 10 millimeter thickness, now that reduced to 5 millimeter, so that case, you are talking about 4 times, factor of 4 reduction in distortion buckling resistance. And that's why the shipyard in the past dealing with 10 millimeter, they don't see much buckling distortion. All of a sudden, I think started from 15 years ago, and you see all kind of distortion issues. So that's one aspect. Another aspect is high strength steel. High strength steel, obviously you got to use a thinner gauge when you introduce high strength steel. In the meantime, reduce stress pretty much proportional to yield strength material. So using shipbuilding terminology, this is essentially A36 steel to, say 36 KSI versus 80 KSI. The residual stress produced, causing Welding distortion is about twice as much. In the meantime, you may want to reduce the thickness from, let's say, by 50%. Now, combining the factor 4, and then you have increased double the driving force, internal stress, we have a big problem. So anyway, again, without getting into detail, so thin section, high strength, much more prone to distortion because you are talking about not just factor 2, not just factor 4, and so that means there's a quantum leap, intrinsic distortion phenomena. So that case, construction procedure become more important, and even more so when we deal with the multi-material structures. So here, I don't want to get into too much detail, but I will try to use a simple analogy, just to drive through a point, say what causing distortion, why, and then how we can learn, derive methodology for effectively control distortion. So here's what I use in my class at the University of Michigan. So if I have a heavy window frame, so I have this support, this is part of the integral part of the frame. The distortion produced step 1 by heating this part, say when we do thermal processing. That could be thermal forming, laser forming, could be welding. That means I'm going to heat up this area, delta T. Since the frame is heavy, we can consider that as a bar situated as in rigidly restrained or fully restrained. If some of you have trouble to visualize that case, we can use the analogy as a fit up. So as soon as I apply heat, this bar, if it's free, going to expand by delta L. This delta L will be alpha delta T multiplied by L0. That's a thermal expansion coefficient multiplied by original length multiplied by delta T. So they are same thing. Applying delta T in the fixed frame, or I have a fit up bar a little bit too long by delta L, right? Since the side area is so rigid, that case they cannot expand. All the expansion will be absorbed locally by this amount delta L by the frame. So that's the simple analogy. And then what we can do is let's just go through some little more details, see what is going on. I'm trying to consider that bar model fully restrained because of the frame is heavy. In actuality, when we do welding operation, this condition is pretty close to reality. We're going to justify that shortly. So that case, I apply delta T for this fully restrained bar, and in that case, say I apply delta T because alpha delta T is proportional. If I assume L0 is unity, so that case strain becomes deformation. So as I heat up, the strain build up in compression will be proportionally. So that means the blue color will be alpha multiplied the red color. And then assuming I reach to a temperature regime below alpha epsilon T less than epsilon Y, because this is compression, so that means less than minus epsilon Y, and then I cool down, nothing happened. I did nothing to the bar. In manufacturing, anything deal with the temperature, actually, we want to change. We go to higher temperature. Then the question is how high, potentially going to have permanent effect. So that case, since this value is alpha epsilon T, that's a compression because it's fully restrained, I equate that alpha delta T equals epsilon Y. That's the elastic deformation capacity of material. So that case defined on the stress strain curve. And then I can find the critical condition. So plug into mild steel. So again, roughly this is consistent with the material handbook, say 30 KSI mild steel, and then the thermal expansion coefficient, 30 million in terms of PSI, Young's modulus. So what this says is I ended up 154 degrees, even well below our cooking temperature, water boiling temperature. So what that says is this temperature, if I exceed this temperature, I'm going to have a permanent effect. That means I'm going to have a reduced stress. Actually, this temperature is pretty benign, very easy to exceed. In friction stir welding, we work at a forging temperature. That means this temperature can be easily exceeded. That means I'm going to have a reduced stress. I'm going to have a permanent effect. So keep this in mind. Even though this is a very simple exercise, we can establish a critical temperature we call delta Y, delta Ty. That stands for the yield temperature. Temperature for the temperature increase to yield steel under fully restrained condition. Okay, fully restrained. So I expand that example a little further. So if I continue to increase temperature now beyond delta Ty, and then what happens is because of fully restrained, some of you may not follow with me, but at least you can work on that later if you're interested. The total strain has to be preserved. So in that case, the total thermal strain, once reached to epsilon Y or yield strength of material, all this shaded color multiplied by Young's modulus, that becomes stress. So this difference, blue minus this horizontal black, I get a plastic strain increasing. Because this is under fully restrained, is under compression, so this is negative. I put a negative on top, so I can use PowerPoint easily to make this sketch. That means this area plus this area equals total strain available, thermal strain available, which is the blue line. Once I exceed delta Ty, I'm going to have a permanent effect. So in that case, on cooling, when I reach to peak temperature, the thermal strain available is here because I ended up elastic strains here. So I move this line in parallel, so I can start to continue to examine cooling effect. During cooling, it goes through shrinkage phase. That shrinkage is elastic before you touch epsilon Y. So that means the reduced stress depends on how much you exceed plus epsilon Y, the elastic limit of the strain in material. Actually, by examination, we know if this distance is equal to this distance, the reduced stress will be residual strain, elastic strain will be epsilon Y, multiplied by Young's modulus, reduced stress will be SY. That means I have yield magnitude reduced stress. Okay, so that's the message. That means we're going to continue, say, assuming that's happening, I continue to heat up the material, producing thermal strain, and the thermal strain become plastic strain as soon as I exceed delta Ty, but I continue to heat up to peak temperature, and then I go through the same process. This time, what we see is on reverse, the shrinkage is beyond tensile yield strength of material, and then I get elastic strain equals epsilon Y, and then I have reversed plastic deformation. So the key message is, as long as this distance equals epsilon Y or delta T equals 2 times delta Ty, I get that's a necessary sufficient condition to develop yield magnitude reduced stress. In that case, the reduced stress will be tensile yield magnitude. So that's the key message. Actually, a moment ago, we talked about 154. So now, if you followed me, and then 2 times 154, that will be 308. That's the necessary sufficient condition on cooling for a system to develop yield magnitude reduced stresses. I tend to get inquiry all the time, say when I do someone doing reduced stress measurement, get a very high reduced stress beyond yield. Actually, that's not a big deal. Reduced stress, as long as you exceed 2 times delta Ty, okay, as long as local heating, we call localized heating, exceed this value, reduced stress will always be equal or larger than material yield strength. Obviously, you have hardening, and that will introduce higher than yield magnitude reduced stresses in terms of peak value. So again, that's the message. Then the question is, how this relate to practice? So I'm using fully restrained 1-bar model. So if I consider a big plate, okay, I'm going to heat up a middle area, make it symmetric, and then we can solve 3-bar model. But without getting into the detail, you just have to trust me. Say what the question is, what takes to reach for delta Ty to reach, what will be the delta Ty, and also how that can be compared with the fully restrained condition. So within this system, I say if the two sidebars has area 2 times the middle heated area, I get a critical temperature. 1 delta Ty is 193. As that size reach to 5 times A2, that means the side area larger than 5 times larger than the middle bar, get 169, 157. So that means in any practical applications, I would say 90% of the time, you satisfy the 154 for if it's a low carbon steel, and so that means 308 roughly, okay, just for argument purpose, very easy to achieve. That's why the NASA's friction stir welded ring, okay, they always above, the residual stress is above yield along the welding direction, triggered buckling. So the residual stress within that area will be tensile, and on the side, they balance it by form equilibrium, and the total area has to be equal to 0, total moment equals 0. Okay. So the message on this chart is 2 times delta Ty criteria. It's pretty easy to reach when you talk about typical structural assembly. Okay, so that's the message. Again, let me extend it a bit because of time. And so actually, what is the heated area? So when we do welding, we have a molten material, and then we have material beyond the weld zone get heated. So this is W2 or A2 here, in reality representing plastic deformation zone. So this is aluminum alloy. That's about 1/4 inch thick. Simulating that process using computer model, so actually the plastic zone far exceeds the width of the weld zone. So again, the key message here is we worry about shrinkage, worry about distortion, not just weld metal. Actually, is the metal surrounding the weld zone, plastic zone. That plastic zone is a shrinkage zone. So that's the key message. Okay, that's simulated by Fernando model. So WP is the width of the plate multiplied by thickness, width of the plastic zone multiplied by thickness. That give me a plastic zone or AP or A2. And if the unit thickness, we call WP. The reason I'm spending a little bit more time on plastic zone is the fundamental quantity impacting distortion. Okay, so with that in mind, again, I don't want to, this is NASA example, this is related to Space Shuttle Station construction, the 2195 tank. So I'm going to bypass that. So if a plastic zone is a characteristic, is a fundamental quantity we can work with to develop distortion control strategy. That case, say why high heat input, low heat input, why low heat input is beneficial. If it's a high heat input, weld is the same, weld size same, filler weld, double-sided fillet. The plastic zone is marked here, anything other than blue, dark blue. If the low heat input, you can see the plastic zone is 1/2 of high heat input. Obviously, as a weld engineer, I think most of you know, we want to have a low heat input, laser is the best, and this provides more mechanics based justification. In the meantime, why we want to reduce weld size? So weld size from 5 millimeter increase to 7 millimeter. This for shipbuilding applications. You can see the plastic zone WP width get increased. Essentially, the total area is doubled, okay, by increasing leg size, filler weld leg size from 5 millimeter to 7 millimeter, okay. So again, this concept been used in 1950s by the Russians, but actually a lot of the people don't do that anymore, but I think they did some classical work in the 50s, so I managed to find the original reference. So how to justify why multiple passes is better than one pass. That's because using chemical etching, so this is from photograph, you mark it up. So this is the plastic zone width, the shaded area is plastic zone size. Identical condition, switch to 1 pass to 2 pass, the plastic zone almost 50% of the top, okay? For fillet weld, single fillet versus double fillet. Double fillet is for the same reason, double pass fillet or single pass fillet. That case give you the distortion because the shrinkage force within the plastic zone, all residual stresses roughly all at a yield, Okay, that means in the out of paper out of the screen direction, you have shrinkage force almost 70% higher than the double pass bot seam weld, and then same thing for a single pass weld, right? So the plastic zone, actually, you can use a computer simulation, you can use chemical etching, metallurgists know how to do that because the plastic deformation is sensitive to some chemicals, okay? So actually, once the plastic zone is known, the distortion prediction is easy. You don't have to do full-blown computational analysis. So here we either call shrinkage force or shrinkage strain-based method. As long as you know the plastic zone size for given manufacturing process, as long as that delta Ty temperature already exceed 2 times delta Ty, that zone is defined. Within that zone, the shrinkage force will be, this is a SY, that's the yield strength of material multiplied by the area, giving the shrinkage force. Once I know the shrinkage force, I can go to different, structural mechanics solution. Obviously, for this case, beam bending problems, I can go to, say, the average longitudinal shrinkage and also rotation of the beam, deflection, can all be calculated by structural mechanics principle. If the shell plate structure, you use shell plate theory. If you don't have a theory analytical solution available, you plug in the shrinkage force or shrinkage strain using Fernando model. So the key thing is FP epsilon Y, right? FP related to AP, E epsilon Y is material property. So that's the key. Obviously, we assume a material has no hardening. If you are more comfortable, say, to take what we call flow stress, that case, that can be done easily. But in concept, much easier to argue using SY to make a point. So with that in mind, let me quickly show you some example. So what would be the distortion control, implication on distortion control? We introduce plastic zone, we call shrinkage zone. Within that shrinkage zone, elastic strain is at epsilon Y magnitude. That, as a result, the residual stress will be SY magnitude along the weld. Actually, those strain get used in literature, they call different names. I have no idea, the eigen strain, inherent strain, incompatible strain. Obviously, I call it shrinkage strain. So what is shrinkage strain magnitude? As long as you achieve 2 times delta Ty criteria, that's epsilon Y. In terms of stress, that will be SY. So that case, they make it a little mysterious, but in my term, just shrinkage strain once you reach to critical temperature delta T. So now, up to this point, so how are we going to control distortion? Let's control shrinkage zone. You want to make a shrinkage zone, the plastic zone, as small as possible. You want to make the shape, the plastic zone, as symmetric as possible. And then here's the more difficult one. The position of the plastic zone, the neutral axis of the plastic zone, the shrinkage zone, got to be as close as possible to neutral axis of the component at that moment in time during assembly. So very easy, shape, size, shape, position. Position is a design problem. Design engineer need to be aware the shrinkage phenomena. So designer should try to put the weld to a neutral axis to a symmetric position as much as possible to make the weld seem as symmetric as possible. So again, here let me clarify and then use a few examples. So in industry or academia, people tend to get making confused statement. When we say shrinkage versus distortion, they are not the same thing. Shrinkage mode has a mechanics connotation indicating fundamental phenomena can be illustrated by simple mechanics model. Distortion is a manifestation of a structural, the shrinkage phenomena in a structural context. So this is a loosely called distortion type that is really describing geometry or out of tolerance geometry. Shrinkage mode is a simple mechanics argument. So let's use a plate, let's say with the bottom seam weld. Only 2 shrinkage, delta L, delta W, just that simple. If everything is, if no other phenomena, if the weld position is symmetry, that means left and right, same area, you only have this shrinkage available for a thin plate. As long as the penetration, the fusion, the plastic zone is symmetric with respect to the weld center. In that case, you are not talking about distortion, but talking about simple shrinkage. That shrinkage is very minimal. But the problem is, when we talk about distortion, that means when the shrinkage no longer has a symmetry to work with, that case we can have out-of-plane distortion, rotation, that's angular distortion, longitudinal bow, buckling, and then in-plane rotation. If the seam located away from the symmetry, okay, you have an in-plane rotation. If a big blob of bot seam weld gets deposited, if the dashed line is not a vertical, not a symmetric to the neutral axis of the mid plate thickness, you have angular distortion. Into the paper, this will develop longitudinal bow. So that means in literature, when we talk about those distortions, they are really reflected unsymmetric shrinkage, okay, causing all those complications. But actually, the pure shrinkage, okay, they are just like what is in the middle of the picture. So with that, so if I look at a single V joint, the illustration for illustration purpose, the red line here is a plastic zone shape because it's not symmetric to the neutral axis of the plate. So you have angular distortion, and also the centroid of the shrinkage zone, the plastic zone, above neutral axis, you get this longitudinal bow. This is the actual experiment done in France and to support the international round-robin study. A few examples, so say why one-pass weld is not desirable. Obviously, for Detroit, for automotive application, you want to have one pass because of high productivity. But sometimes you may have to compromise. It depends on what is the priority. So one pass versus two pass versus three pass. So that case, three pass will be better, the best, better, that's the worst. Okay, that's because the plastic zone is a symmetry. And then some of you may ask, how about I just deposit pass one? That's unsymmetric. That's how clamping come into work. Okay, so that's a situation. Jill, do I have a couple more minutes? Just walk. Jill?
Yes, I think you can keep going. Anyone that will jump off, and we'll follow up with the recording afterwards. So you can keep going.
I may need 10 more minutes. Is that okay?
Yes. Go ahead.
Okay. So how are you gonna say with during deposition, pass one, pass two? How I'm gonna maintain symmetry? Because when I deposit pass one, it's not a symmetric. The plastic zone will be something like this. In that case, you use clamping. Clamping to provide restraint to maintain, because you don't have a symmetry, you need a fixture to control things, which we're going to get into later. And then once it's done, plastic zone is symmetric, you can unclamp it, you can take out from fixture, and then you have stability. So again, when I say they don't have to be perpendicular, they can be, only thing we require, like a double V, is a symmetric with respect to the neutral axis of the mid thickness. Okay, so that means double V work better, but you need a clamping. If I use clamping, you don't need to do this sequence 1, 2, 3, 4. That's not necessary. I can do 1, 2, 3, 4, or any other scenario as long as I have clamping system to keep things in place. Okay, so this is the one narrow groove weld from one of the major utility company for pressure vessel fabrication. So you can see we don't need to do measurement. So you know this one, why that's because plastic zone roughly proportional to the fusion zone. So they give you strong, very severe angular distortion. This is a narrow gap with a good clamping after welding, and you can see virtually no distortion, right? So anyway, just as a summary, I already repeated, but just to elaborate a few more things. The control of the plastic zone or shrinkage zone in terms of position, size, and shape is very important. Again, try to emphasize, I think as a weld engineer, we need to inform designer positioning of the weld is a design problem. Okay, that means you want to maintain symmetry. And once you have a symmetry, you want to be as close to neutral axis as possible, and other things. I'm not going to get into detail, okay? And then in process, I already talked about clamping, and I'm going to do some illustration. So I'm going to bypass a few things. Say for filler weld, so convention in some of the industry where we use size as a measure of filler weld because it's something measurable outside. We don't count penetration, filler seam weld. So from distortion point of view, obviously this is not good because you want to make sure they come into the neutral axis. So with a little bevel, and that gives you improved distortion control. And then if I do fully beveled, in that case you get the same leg size, equivalent to regulation, like by safety regulation, government regulations like offshore structures, and you satisfy those criteria, but you are close to neutral axis. Okay. Obviously, a better one today with a hybrid laser welding, and you achieve that with a minimum leg size. Actually, for this particular case, you don't need any leg size. Okay, but so that's some of the examples. Clamping is important. Clamping, just clamping anywhere, has to be clamped at the right location. So this is the example showing, say, without clamping, with clamping, how much improvement. But when I work with the industry, people telling me, say, they are using clamping. Okay, so obviously this clamping doesn't follow any principle, and this is happening on a daily basis in different industries. Okay, I want to use that example to give you a sense. Clamping sounds like so non-technical, but in reality, it's a very technical term if you want to do it right. How to do it right? Here showing you example. Obviously, this is 2010 related to one of the manufacturing company. So this I get angular distortion. How about I jammed up below the filler weld, and then I do pre-cambering, essentially pre-bending, okay? But that did not work. After releasing the bending, you can still get the distortion. That means this clamping, not clamping in the right location, too far away from the action zone. What is action zone? Plastic zone coupled width of the weld width in this regime. That means you had to go in, clamp that area. Obviously, it's a little bit difficult. But to illustrate that, say for this particular stiffened panel, so the plastic zone is in this neighborhood, about a couple times the filler size. That means as long as I clamp this regime, okay, that will be most desirable. But obviously too close, you're going to interfere with the welding. That means the question is how far away I can clamp without interfering with welding. So this is what this research, we did some quick calculation. We found we can do 5 inches spacing, still can hold this area. The reason you want to clamp close, look at the red color. This is a computer model. That means this part, just like when you open door, there's a plastic hinge. That hinge serves as rotation. The rest of them is rigid body motion, and actually the action located all in this yellow region. That means you want to clamp as close, not a yellow region, the gray area. You want to go as close as you can. Actually, this company, they got the idea, immediately implement, compare with the reference, and then they have a clamping. That's about 5 inches to 6 inches. You can see virtually no angular distortion. Okay. So again, quickly, just a few more minutes, come back to this picture. So now I think I can elaborate. The reason this distortion cannot be fixed because of lack of torsional rigidity in this direction. This one doesn't matter what a sequence, welding sequence, what fixture you're going to use. It doesn't. You're not going to be able to do it. They're always going to have this distortion, right? So that's the situation. What do? We have to implement temporary support. So look at those angles, okay? Those angles, essentially triangle give you ship rigidity. So that means you temporarily, because of poor design, you introduce those, every 10 inches, provide those angular iron, for this particular case, stainless steel, provide support so you can have a shape. Once you have a shape, rigidity, stability, then you can manage sequence. So without doing any measurement, this is a similar component, but it's rotated. So left to right, you can draw the observation. Say that's much better, significant improvement. Actually, this one on the right, without require any corrections. Left-hand side is wasted. Okay. So anyway, again, I exceeded time a little bit because I think we struggled when we set up the meeting, set up the webinar. This would be my takeaway message. Again, those I think it's very simple argument. Delta T larger than 2 times delta Ty. Now, delta Ty is easy to calculate because that's Sy divided by alpha E. Okay, that's in the previous page. This condition pretty easy to achieve. Doesn't matter the friction stir welding, arc welding. You achieved it. Okay, that means longitudinal stress. Okay, the peak value is going to be yield magnitude. Depends on hardening behavior. You can exceed yield, so that's not surprising. So don't get too excited. The question is how to mitigate that effect. Okay, so you're going to have high reduced stresses as long as you have this condition satisfied. So that case, within the plastic zone, we call shrinkage zone, that zone causing all the trouble we are talking about. Okay, small, large, different industries, they introduce all the trouble for us. Okay, so that case, here's the key message is the most effective control of distortion is in process because you don't have to overwork as long as you have the right procedure. That means, again, I already illustrated through various examples. You got to use a fixture if you don't have good symmetry. Even if you have symmetry, you can use multiple welding tools, but with the fixturing has to be properly applied. And because to maintain overall geometry, that's just like this example. Okay, this even doesn't have any symmetry. In the meantime, prevent the plastic zone hinge effect. That's the rotation. That means you got to do clamping. That clamping has to be properly designed against plastic zone. That means you need to know where the plastic zone located. Once that gets done, this is through process planning, and then you want to make sure plastic zone size as small as you can, shape as symmetric as possible with respect to the neutral axis of the component you are working with. And then for your designer, your design engineers need to consider how to position weld. The weld has to be positioned as close to symmetric axis, neutral axis as possible. And also procedure has to be symmetric. So I use multiple pass weld, you use clamping, and even though you don't have the symmetry, but in that case you can implement procedure symmetry. Okay. So if this in process doesn't cost much, and the post process, if that's still not good enough, that means actually what a causing reduced stress yield magnitude because epsilon Y or epsilon F, that's flow stress or yield strain or flow strain, they got produced in the plastic zone or shrinkage zone. Whatever you can do to stretch it, okay? That's why hammer pinning, you not stretch, you compress it, so you get elongation in the lateral plane, you can reduce. You don't need to introduce too much, okay? And sometimes you can introduce a new plastic zone to counteract the weld shrinkage zone. So that's just roughly what again, I bypass some of the charts. You're gonna have a copy, but they just give you some flavor and some general message in terms of how you can implement in practice. Covers a little bit of design and also assembly procedures. Joe?
Thank you very much, Dr. Dong. Thank you. Very good presentation. Certainly appreciate you taking the time. I know we had some technical difficulties. Appreciate everyone sticking with us. However, in the meantime, if we did have questions, I think we can take a couple from the audience. While we have a few minutes left, I don't want to go too far over. But I want to make sure that people do have a chance to ask questions. So if you do have one, you can fire away, or you can type one in on the chat function, the GoToMeeting chat function to the organizer, and I can facilitate it there. So let us know if you do have any questions. While you're thinking of questions, I do want to remind you of next week. If you do happen to be in the Detroit area, come on by and register to our technology and tour event going through our melt process projects. And a tour of our high bay coming up on the 15th from about noon to 5. You can find that under our events section on lift.technology website. Do anyone have any questions for Ping Shaw?
GT just wants to say thank you very much, gentlemen, for your time, and we appreciate it.
Thank you very much for joining me. I certainly appreciate that. Well, if there are no questions, I think you can contact Dr. Dong via his email that he had at the very beginning of the slide, and I will follow up this webinar with a recorded version so folks can take it back and follow up there and watch it again and send it to folks who may have encountered some technical difficulties. So thank you very much for joining today. We certainly appreciate that. Ping Shaw, thank you very much for your presentation, and stay tuned to your emails for our next presentation, and hopefully we can see you here at LIFT next Tuesday to go through some of our other projects. Thank you so much, everybody.